Hello, my name is James Brawley. I'm a student at CSU Global. This is a presentation for my mathematical modeling class. We'll be presenting the SIR epidemic model. First, some terms that you're going to need to know. Susceptible. So someone susceptible to an infection in a population is going to be represented by this smiley face white poker chip. They have not gotten the infection yet, and so they can get it. An infected person is going to be represented by a red poker chip with a sad face. This is someone from the susceptible population that has been infected. And then a blue poker chip with a just sort of blah face is going to be someone removed. And that is someone that was infected and then is removed and cannot be infected again. So the total population is just going to be a combination of susceptible, infected, and removed individuals. So S plus I plus R equals N. Here's a visual example. So we have 20 people. So N equals 20. The total population is 20. At time 0, 1 person is infected and 19 people are susceptible. During the next time step, that person that was infected 2 susceptible people, and they became removed from the population. That leaves 17 susceptible people. Okay, as we keep just progressing by time steps, you'll see 4 new people became infected that were susceptible. The 2 that were infected in the previous time step have become removed. And that leaves 13 susceptible people. Okay, again, same situation. Everyone that was infected 2 susceptible people. Infected people became removed, leaving 5 susceptible people. By the next time step, every susceptible person has become infected. There's still 6 infected people in this population and 14 removed. And by the next time step, everyone has been removed from the infectious population. All right, so that's just a visual for how the SIR model works. We're going to go into some more detail. First, if you build a flow diagram for this model, you have susceptible people. Susceptible people can become infected people, and infected people can become removed people. So there's no way to go back to being susceptible unless you're in the susceptible pool. But some additional terms that we need to define are beta, effective contact rate. So if someone's infected, just because they come into contact with someone doesn't necessarily mean that they're going to become infected. So there's going to be a rate at which that happens. Delta, duration of infectivity. So once someone has become infected, how long are they going to be infected before they can become removed from the population? So if we add these additional terms to our flow diagram, susceptible has nothing going into it, only people being removed from it, and that's at a rate of beta times infected. So the infected rate times the infected times the susceptible divided by the entire population. So that's a proportion. Infected people either have people coming in from the susceptible group or going out to the removed group. People coming into the infected come at the same rate that they were leaving the susceptibility group, which makes sense. And then the people leaving the infected group, they leave at a rate of 1 over delta times I. When we take our flow diagram and create a discrete dynamical system, we get these 3 equations. So again, susceptible at any time t is going to be equal to the number of susceptible at t minus 1, the previous time step, minus the effective contact rate times the infected at t minus 1 times susceptible t minus 1 over n. All right, just that function that's between the susceptible and infected group. Infected, it's a little more complicated, the equation, because we have the people coming in from the susceptible group at the same rate they're leaving, but we also have the infected from the previous step minus 1 over the duration of infectivity times the infected. And then finally, for the removed group, it's going to just removed at time t, it's going to equal the removed at t minus 1 plus those people coming in from the infected group. All right, 2 examples. So I just took those discrete dynamical systems and implemented them into the spreadsheet you see. On the spreadsheet, there's user inputs, 5 of them. There's one for the total population, one for the effective contact rate, and one for the duration of infectivity. And then you also have to input the number of affected initially and the number of removed initially. The number of susceptible is just going to be the total population minus number of infected minus the number of removed. And so for this example is the first one out of the textbook. So given removed at time 0 equals 0, total population is 5,000, infected at time 0 is 5, the effective contact rate is 0.9, and the duration of infectivity is 5. Okay, when you graph the spreadsheet, this is what you get as a result. So to answer the questions, approximately when was the epidemic at its worst? And that would be at day 13. Escape out of this for a second. So day 13 is right here. B, how many people were sick at the peak of the epidemic? So if I came across here, or actually if I go to the spreadsheet, I can show this even better. If you hover over the graph, at day 13, 2,488 people were infected. All right, C, approximately how long did the epidemic last? So I just went into the spreadsheet, rows 62 and 63 went from 1 infected to 0 infected. So at time 55 is how long? So 55 time steps or 55 days is how long the epidemic lasted. Approximately how many people contracted the disease during this course? So in the third column here, you can see 4,975 are removed, so they at one point had been infected. Okay, similarly, I didn't have to rebuild my spreadsheet because it's using the same set of equations. I just changed my user inputs. So this is example 2 from the textbook. Given removed at time 0 is 0. Now the population has decreased to 3,000. Initial infected is 10, so that's 5 more than the last example. Effective contact rate is 1.6, so that's 0.7 higher than the previous example. And the duration of effectivity is 2, and that's down 3 from the previous example. So when I input those into the spreadsheet, and I go to the spreadsheet, approximately when was the epidemic at its worst? So I'm going to go back to the actual spreadsheet so we can see this. Move my face. Okay. So for this one, when I click on the red line, it's going to be at time 8. It sort of matches where the removed are, and it's going to be 1,191 people. Okay, I'm just using this dot on the yellow because it corresponds to the peak of the red, because the red did not have a dot there. All right, numbers or part C, approximately how long did the epidemic last? So again, I went to the spreadsheet. Between day 21 and 22, infected went from 1 to 0, so I say that the epidemic lasted for 22 days. Approximately how many people contracted the disease during the course of the epidemic? So at day 22, 2,956 people are removed from the population, so that's how many at one point had been infected. All right, now I hope this gives you a really quick example of what the SIR model is about and give you a chance to implement it into a spreadsheet and use the results to do some analysis. All right. Thank you for your time.